Good evening, everyone. My name is Kim Strong, and I'm the chair of the physics department here at the University of Toronto. Welcome to our 2023 J. Tuzo Wilson Public Lecture. I'd like to start my remarks with the official U of T Statement of Acknowledgement of Traditional Land. I wish to acknowledge this land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and most recently the Mississaugas of the Credit River. Today, this meeting place is still the home to many Indigenous people from across Turtle Island, and we're grateful to have the opportunity to work on this land. This statement always seems appropriate when we're giving a lecture like this, all about the Earth. As many of you know, the J. Tuzo Wilson Public Lecture is an annual event put on by the Department of Physics at U of T. Each year, we commemorate the life and work of John Tuzo Wilson, who was one of the key discoverers of plate tectonics. Plate tectonics is to geoscience as Darwinian evolution is to biology. It's a framework into which everything else fits. Tuzo Wilson's association with the Department of Physics goes back to his undergraduate days. In 1930, he was the first Canadian student to graduate in the field of physics and geology before heading to Cambridge, then Princeton, the Geological Survey of Canada, and the Royal Canadian Engineers during World War II. In 1946, he received a call from Professor Burton, who was the head of physics at U of T at the time, asking if he would accept a position as professor of geophysics in the Department of Physics. He accepted and moved to Toronto in June of 1946, becoming the only professor of geophysics in Canada at that time, I believe. Just after World War II, very few of the world's universities had any significant specialization in geophysics, and none in Canada except Toronto. Over the following 2 decades, working out of an old house at 49 St. George Street, Tuzo Wilson led and inspired a group of geophysicists here that was unique in Canada and notable globally. Something like 80 graduate students graduated between 1949 and 1980. Apparently, those who worked on winter weekends at 49 St. George had to shovel coal into the furnace to maintain a reasonable temperature. So things have improved in some ways, even if our building does have issues. So Wilson's life ambition was to understand global geology, and from 1961 to 1967, he became a major player in creating plate tectonics, the new global view of how our Earth works. He remained in his position in the physics department for almost 30 years, during which time he made a series of famous contributions to the ideas of ocean floor spreading and continental drift, and was an acknowledged leader in the study of the Earth. His influence extended well beyond geophysics. He was appointed as the first principal of Arundel College, now the University of Toronto at Mississauga, apparently entertaining some 10,000 guests in his home over a period of 7 years. My mind just boggles. He also served as the president of the Royal Society of Canada, Director General of the Ontario Science Centre, and Chancellor of York University. He was a man of many interests. So we commemorate Tuzo Wilson and his many contributions with his annual lecture, and also with the J. Tuzo Wilson Professorship in Geophysics. This professorship is awarded to a geophysicist at U of T for a 5-year term. The holder presents an inaugural lecture during the first year of their appointment and organizes a public lecture by a distinguished geophysicist for the subsequent 4 years. So I'm very pleased to introduce our current J. Tuzo Wilson professor, Chinya Liu, who is cross-appointed in both the Department of Physics and the Department of Earth Sciences. Chinya is a computational seismologist who uses seismic data to probe the structure of the Earth's interior. And in this, she's a very fitting successor to Tuzo Wilson. So I'll now pass the microphone to Chinya to introduce our speaker for the evening.
Well, good evening, everyone. Welcome to this very beautiful theater. Actually, after, I guess, 3.5 years of online experience or not having the Tuzo Wilson lecture. My name is Chinya Liu. Like Kim said, I actually have the honor to be the current J. Tuzo Wilson Professor of Geophysics at both Department of Physics and Department of Earth Sciences. So today I have the extraordinary pleasure to introduce our Tuzo Wilson lecturer this year, Professor Roel Snieder. Roel is currently W.K. Keck Distinguished Chair of Professional Development Education at Colorado School of Mines. So he received his master's degree from Geophysical Fluid Dynamics Laboratory at Princeton, which, as you might recall, is the lab where Professor Manabe worked, who was the 2021 Nobel Prize winner for physics. So Roel received his PhD in seismology from Utrecht University in 1987 and became a professor of seismology there in 1993 before moved on later to Colorado School of Mines. I'm not going to spend 10 minutes listing all the accomplishments and services that Roel had for the community, but just a few highlights. In 2000, he was elected the Fellow of American Geophysics Union. 2011, he was elected the honorary member of the Society of Exploration Geophysicists. And 2016, he received the Beno Gutenberg Medal from the European Geophysics Union, and he got the Outstanding Educational Award from the Society of Exploration Geophysicists. He's also currently the director of Center for Wave Phenomenon at Colorado School of Mines. So Roel is really well known for putting his great scientific intuition and theoretical insights to work on the diverse range of geophysical and seismological problems, ranging from early days of surface wave scattering theory, ray perturbation theory, seismic interferometry, engineering seismology, machine imaging, etc. Just to give you an idea, he's got more than 500 publications, which with an H index of 80. Just to give you an idea for seismologists, H index 80, that's astronomical. So that's just speaks to the scientific contribution of Roel. But actually, Roel is also in recent years very well known for his contribution to educational outreach, public talks, and professional development. On his website, he lists a range of public education topics that he constantly give out, and he actually this afternoon just gave a professional development workshop to a bunch of graduate students, including me, on time management, which I felt learned quite a bit from. I wish I had when I was a graduate student. He's also the author of textbooks that are a bit outside of the range of typical seismologists, things like A Guide Tour of Mathematical Methods for Physical Sciences, and The Art of Being Scientists, and The Joy of Science. So we're very, very honored to have Roel here, and he'll tell us a bit about carbon capture and sequestration today. So let's give him a very Torontonian welcome.
Sound is on? Good. Yeah, thank you for your kind introductions, Kim and Chinya. It's a pleasure to be here in Toronto. It's been probably like 12 years since I was here. Weather is still gray, I've discovered. But I love talking about this topic because this is a topic where sort of technology meets society. And I think we're facing some interesting challenges, as I will point out in this presentation, and our social response is going to determine very much to what is going to happen. So we're going to talk about carbon capture and sequestration. That's sort of a complicated way of saying, catching CO2 if you want, carbon dioxide, and injecting it in the subsurface. And I'm going to talk about sort of the degree to which this may help us or not. So we're going to talk about energy. I'm going to show you a lot of graphs with projections. Projections are all a little bit shaky, but we do the best what we can. This is a graph of the worldwide energy use from 2010 to 2050. So the last 30 years are obviously scenarios that are played out. This is by the Energy Information Agency. That's a big international organization that makes scenarios for worldwide energy use. And you can see that our energy use is still going up. This is largely driven by population growth and by also countries who are aspiring to have a style of living like we have in North America. And you can see how sort of the different sources of energy contribute. So you can see that nuclear is relatively small, less than 10%. And you get coal, natural gas, petroleum, and renewables. And the biggest growth in this, of course, is in the renewables. So if you take together the coal and the natural gas, they're called fossil fuels. Right? And we call it fossil fuels because literally it's like we're using fossils. We burn them. I mean, either in a solid form like coal, in a liquid form like petroleum, or in a gas form like natural gas. And so all of these fuels, when we burn them, they produce a lot of CO2, and that drives climate change. It's very interesting to split it out between the countries of the OECD and of the non-OECD countries. So OECD, that's basically North America, Europe, Australia, New Zealand, Japan, several South American countries. And you can see that in the OECD, the projected energy increase is pretty flat. That's also because the population is flat or even declining. And we also are becoming more and more clever in using energy. But you can see in the non-OECD countries, we are projecting a big energy growth. Some of it is sort of driven by an increase in renewable energy, but as you can see, there's also a quite expected change in the use of fossil fuels. So, of course, this is bad news for climate change. So let's talk a little bit about how we use energy. And you probably think about the purposes of energy that you see on these slides: transportation, heating, power generation, and of course we use a lot of energy for that. But there's also other sources for which or other purposes for energy and hydrocarbons that you might not think of. For example, food production. Our food production has become completely industrialized. We use about 1 gallon of petroleum per person per day for food production. It's pretty amazing. And a lot of that is used by creating fertilizer, which is a very energy-intensive project. Then we also use hydrocarbons for just plastics and other materials. You will not believe what you put in and on your body that is made out of petroleum. And lastly, I want to mention information technology, because all these things like uploading a picture in the cloud, it looks like a harmless activity that takes little energy, but it actually takes significant energy to do all of that. This graph just blew me away. It compares the energy that we use worldwide for computing, and that's indicated by the blue bar, and it puts it in a ranking of the energy use of different countries. So you can see that the energy that we use for computing is now larger than the energy use of India or Germany or Canada or France. Right? So even though it looks very clean to use your computers and to upload something in the cloud, which sounds like a nice ethereal, clean concept, it actually requires significant energy. And actually, and this shows us how crazy we are. Here you see the amount of energy that we use for mining bitcoins. And the units are complicated here because they are terawatt hours. But if the red arrow here is 0.5% of the world's electricity production. And you see here in the different curves, they give different estimates of the amount of energy that we use to generate or to mine bitcoins. Right? You can see that depending on which scenario you believe in, about between 0.5% and 1% of the world's electricity use is being used to mine bitcoins. I mean, a bitcoin is nothing, right? I mean, are we out of our minds? Yes, we are in certain ways, I think. With apologies for all of you who own bitcoins. So, of course, this leads to all this energy use, and especially the use of fossil energy, leads to the production of carbon dioxide. It's a greenhouse gas, and that's the main driver of climate change. And this is a graph that shows the last 10,000 years. It shows the carbon dioxide concentration in the atmosphere over the last 10,000 years. The units are parts per million, so that is for every million molecules you may have let's say 300 carbon dioxide molecules. And you can see that up to recent times, the carbon dioxide concentration in the atmosphere is about 260, 280 parts per million. And then you can see this big increase all the way on the right. This is called the hockey stick curve. And this is how quickly the carbon dioxide concentration in the atmosphere is changing, mostly by man-induced emissions. So this is called the hockey stick curve for obvious reasons. And so if I was Al Gore, you would see me now on an elevator and saying the carbon dioxide goes higher and higher and higher. This plot, which is from 2007, is already outdated. We've passed 400 parts per million. I think we are at 420 or something. Do you know? 420? Okay, expert here says 420. 420 parts per million, right? So it's not quite doubled yet, but we are on our way for doubling the amount of carbon dioxide in the atmosphere. It's very interesting to compare the use of different countries or how different countries emit carbon dioxide. So on this horizontal axis, the width of every bar is the total amount of carbon dioxide emitted by the country. The height of every bar is the carbon dioxide emissions per person, per capita. So you can see on the left we find the Middle East, they are the champions. Then I'm sorry, Canada comes right after it, very close to the United States. Then we get to Australia, etc., etc. You can see that China is a big emitter right now, but per person they emit much less than we do in the Western world. So you can imagine what's going to happen if China really adopts a living standard and an energy use like we do in North America. The amount of carbon dioxide emitted by them would be much larger. I also want to point out, I also put in the carbon dioxide emitted by doing one intercontinental flight, because flying is probably the worst thing you can do when it comes to climate. In fact, I was in doubt whether to come here because of the flying that I would do, just of the climate impact. And I think we should start thinking about those issues. And I decided to come after all because I think education is also really important. So that's why I'm here. But one round-trip intercontinental flight produces about 1 ton of CO2. And in North America, the United States, Canada, we produce about 12 to 15 tons of CO2 per person. So you can imagine what one flight does to it. And it's not because planes are so energy efficient. Per mile you use about the same amount, you produce about the same amount of CO2 whether you fly or whether you drive, order of magnitude. The problem with flying is that you make so many miles, right? And that's why you produce so much CO2. If you look at the United States, we can see a big change. You can see that the production of natural gas is steadily increasing. That is largely driven by our ability to do hydraulic fracturing. It's very interesting that most European countries don't want to do hydraulic fracturing, but they are now importing LNG gas from the United States. You also see that the coal production is declining, right? So that you basically have two curves that go like this. So we are slowly replacing coal by natural gas, at least in North America, although in Germany right now the reverse is happening because of the war in the Ukraine. And why is that important? That is important because per unit energy that you produce about twice as much CO2 if you burn coal than if you burn natural gas. And the reason is very simple. I'm not a chemist, right? So all the chemistry you're going to get from me is extremely simple. It's sort of the chemistry, I can wrap my brain around it. If you have natural gas, it's basically methane. It's one carbon atom and there's 4 hydrogen atoms around it. So when you burn it, right, you produce one molecule of CO2 and you produce 4 molecules of water. And a lot of the energy comes from basically burning the hydrogen to give you water. Whereas if you have coal, you have a long carbon chain, and for every carbon atom, there's only 2 hydrogen atoms. So more of the energy comes from basically connecting the carbon to the oxygen than from connecting the hydrogen to the oxygen, relatively speaking. So, switching to natural gas from a climate point of view is a great thing, although you can also argue that all the methane that you release into the atmosphere by producing the natural gas, that may offset it. But let's not go there. So this leads to climate change, and I know that there's still plenty of people around that is who argue that this is an unfounded myth. But this story has been around for a long time. This is from a paper from 1896 from Arrhenius. Some of you may have heard from Arrhenius' law, which gives you the speed of chemical reactions. This is a very complicated table. You cannot read the numbers. But he looked at this problem. He asked himself in 1896, if I double the amount of CO2 in the atmosphere, what's going to happen to the temperature on Earth? So he didn't have computers, he didn't have climate models. He used some very simple equations for energy balance, but they were pretty advanced. And I'm just going to highlight the numbers that you see in the red box here. They're shown over here. So this is the climate change in degrees Celsius that Arrhenius predicted in 1896 as a function of latitude. So he was right and he was wrong. I mean, he was right in the sense that he predicted a larger change at the high latitudes, so when you go closer to the North Pole or to the South Pole than when you are closer to the equator. And that is because he took into account also the fact that if you change the temperature, you change the amount of ice in the polar regions, and thereby you change the reflectivity of those regions for sunlight, and thereby you change the energy balance. He was wrong in the sense that he overestimated the change with about a factor of 3. So he got some of the numbers wrong, but basically he got the big picture right. And so now, of course, we have much better models. And so this is Suki Manabe, who you just mentioned. I had the pleasure of taking classes from him. He's a world-renowned climatologist at Princeton University, and he has a wonderful book called Beyond Global Warming, in which he describes all the numerical models that have been used to study climate change. So subtitle is How Numerical Models Reveal the Secrets of Climate Change. And this is one of his papers. This is from the 1960s, so also quite a while ago. And you can see here, according to our estimates, a doubling of the CO2 content of the atmosphere has the effect of raising the temperature by about 2 degrees Celsius. And that number hasn't changed much, even though their model was, a lot of assumptions went into their model. And you might think, well, 2 degrees centigrade, you know, I mean, who cares if it's in the summer, if it is, let's say, 24 degrees centigrade in Toronto or 26 degrees centigrade in Toronto, right? Not a big deal. But the big deal is, of course, that once the energy becomes more energetic, weather really starts to change. And of course, we have seen changes in, pretty dramatic changes in the weather, you know, big drought in the western part of the United States, crazy storms. I live in Colorado. You know, wildfire season was from April through September. Basically, wildfire season is now much longer. And so a lot of things are changing right now. And that's because the climate variability changes when the average temperature goes up. And so here you see another picture of the change. This is the extent of the Arctic sea ice in 1979 and 2021. This is in September, so that's the time of the year when the Arctic sea ice is at the smallest extent. And you can see in the lower plot that across northern Russia, offshore of Siberia, basically water was gone. Willem Barents could have sailed all the way now from the Netherlands to the Far East. Another consequence of climate change can be sea level rise. According to current model, the expected temperature increase leads to about an increase of 40 centimeters of sea level rise. You might think, what's the big deal? The big deal is that the very darkest red colors in this map of Florida would be submerged. That's the average sea level rise, right? I'm not talking about hurricanes, storms, and all other things. And you might say, well, yeah, you know, that's a thin strip along the coast. It is. I also put in this image, nighttime image of Florida, and of course you can see along the coast that's where people live because they want to live close to the sea. So this is driving some changes in society, and we're seeing this happening right now. Some of you may detect a foreign accent when I speak because I'm from the Netherlands, right? And I show a map of the Netherlands in the left panel. And already half of the country will be underwater because, you know, the Dutch are crazy in building dikes and reclaiming land. They worried about changes in sea level height, but you know, the Netherlands is an affluent country, especially since we still produce natural gas. So the Dutch are raising their taxes to raise their dikes. They're in good shape for now. But now think of countries like Bangladesh. You know, the current estimates of sea level rise predictions are that 25 million people in Bangladesh would be displaced. If you know where these people can go to, they would love to hear from you, right? Because where can they go to? Right? Is India going to embrace them? Is Myanmar going to embrace them? Some really big challenges out there. A topic that is not often talked about is sort of ocean acidification. So if the amount of CO2 in the atmosphere goes up, the ocean water becomes more acidic. And a lot of life in the ocean is basically built on calcite, on calcium shells. And this is an experiment done with a pteropod. I don't know what a pteropod is, other than that it's a little microscopic organism that has a little calcite shell, which was put in water which has the same pH as what we expect for the year 2100. Right? And it was kept in there for 24 hours. And what you see in the upper panels is that the edges of that shell are becoming serrated because the shell is literally dissolving in the seawater. So, climate change doesn't only affect the temperature on Earth, it also affects the composition of seawater, and therefore much of the life in the seawater. And these sort of animals are at the base of the food chain. Okay, so now I probably have really depressed you. Right? I also have good news, I also have good news. But it does raise the question, okay, now what? What are we going to do? Are we not going to do anything? Are we, what are we going to do? And some of my colleagues, they're very much infatuated with carbon capture and sequestration. This is a paper from the Leading Edge. That's a professional journal of the Society of Exploration Geophysicists. And one of the lines in there is that injection of CO2 into depleted reservoirs is a well-accepted leading mitigation strategy against climate change. And in this talk, one of the cases I want to get across is that before this technology can be a leading tool for mitigating climate change, we have some big questions to answer. So we're going to talk about that. And unfortunately, I will have to dive into the numbers because the devil is in the details. You have to look at the numbers to understand this. And the numbers are sort of hard to wrap our minds around, right? I don't know what 10 to the 9th is. Yeah, I know it's a 1 with 9 zeros, I know that. But I have no mental concept anymore of a billion. Okay? I can count to 100, basically. And most of us have a hard time wrapping their minds around these big numbers. So I'm going to start out by showing you a graph from the paper of Pakala and Sokolov in 2004. So this is an older paper. They looked at different actions that we can take to basically mitigate or to restrict CO2 emissions. So here you see as a function of time on the horizontal axis from 2000 to 2060 projections for CO2 emissions. And the units here are gigatons of carbon per year. Now already we run into the problems. Gigatons of carbon per year. What does that mean? And I'm going to talk about it later. The upper curve is labeled BAU. That means business as usual. So basically, if we go on growing as we expect to grow, you can see the emissions growing there between, let's say, 2000 and 2060 with a factor of 2.5. The lower curve, so that's the curve that delimits the blue area, is how much CO2 emissions we can afford if we want to keep the carbon dioxide concentration under 500 parts per million. So remember, before the Industrial Revolution, the carbon dioxide concentration was roughly 260 parts per million. So it's basically a doubling of the amount of CO2 in the atmosphere. What do we need to do? Well, we need to avoid all the emissions in the green triangle, so to speak. That's our job. Right? That's a big job. We need to avoid about 9 gigatons of carbon emissions per year. Okay, so they said that's a big problem. So how do you deal with a big problem? Well, you chop it up into smaller problems. Oh, okay, I first want to show this. This was 2014. Now we are at 2013. This is a complicated graph, but basically the upshot is that since we haven't done much since 2004, that 9 gigatons of carbon dioxide emissions per year that we want to avoid has now grown to 21. Right? So that's the number that we need to think about. But just to be on the conservative side, I'm going to look at the problem of, okay, let's say we want to avoid emitting 9 gigatons of carbon per year. And so this is what in the paper of Pakala and Sokolov said. They said, well, you know, this is a big problem. How do you deal with big problems? You divide it into smaller problems. Divide and conquer. We do that all the time. Okay, so they basically divided it up in that green area into 7 wedges. So basically, and they identified 15 possible actions that we could take to avoid the emissions in each of these 7 wedges. What would those wedges be? And I'm giving you a few examples. It could be energy efficiency and conservation, not conversation, nuclear energy, renewable energy and fuel, more efficient forest and land use, or injecting CO2 in the subsurface. That's carbon capture and sequestration. And how much do you need to do? Well, if we could generate electricity at 60% efficiency, rather than the efficiencies which we generated now, that would be 1 wedge of energy. If we would cover 3% of the USA surface with wind turbines, that would be enough for the whole world to cover 1 wedge of energy. If we would build 500 nuclear power plants, that would be 1 wedge of energy. Or if we inject 3 gigatons of CO2 per year into the subsurface, that's 1 wedge of energy. So these are big numbers. This is a huge challenge, but you know, we are working on it. We're making progress. I'm going to focus now on that last topic of the 3 gigatons of CO2 per year. So first, let's talk about CO2 sequestration. What you do is you basically take a stream of gas that could be the output of a coal-fired power plant. It could be a cement factory. There's different sources of CO2 that you might capture. You capture it, you separate the gas that you have captured into the CO2 and the other gases, and I'll explain to you in a minute why you need to do that, and then you inject it into the subsurface down to a depth of at least 1 kilometer, and that's because you want to make sure that the CO2 remains a liquid rather than a gas. Because if there's a gas, there's no storage capacity to store the stuff. So it needs to be a liquid. So 3 gigatons of CO2 per year. I asked myself, okay, what is 3 gigatons? Because I don't know what 3 gigatons are. So I looked for numbers that are the same. And you know what? That's comparable to the world's oil production. We produce about 4 gigatons of oil, petroleum per year. So it's comparable, right? So if we want to use one of those wedges of the model of Pakala and Sokolov, we need to inject an amount of CO2 in the subsurface comparable to the amount of petroleum that we produce right now. That's the job. And we produce a lot of petroleum, right? So you probably need to build a comparable infrastructure. How large is that infrastructure? It's gigantic. You know, this is a space image from Kuwait. And I put a blue arrow there. That's one of the main oil fields in Kuwait. It's completely riddled with wells and infrastructure, right? And this is just Kuwait, but there is, you know, the United States, there is Saudi Arabia, there is the North Sea. I mean, the infrastructure that we have in place now for producing petroleum is gigantic. We probably have to build something similar if we want to sequester, store 3 gigatons of CO2 per year in the subsurface. Okay, so what has happened? Because there have been quite a few projects. This is a complicated graph, but again, time runs from the left to the right. So basically, we go from 2002 to the present moment. So this is the projects that were planned for injecting CO2 in the subsurface. Now, this is a complicated graph. The size of the circle gives for each of these projects how much energy is going to be injected. How much tons of CO2 are going to be injected in each of these projects. The largest circles that you see here is about 5 megaton. So a megaton is about a factor of 1,000 smaller than a gigaton. So if you have a project where you inject 5 megatons in the subsurface, you need 200 of those to make 1 gigaton, because you need to upscale it with a factor of 1,000. And you can see that most of these planned projects then were coal related. Those are the ones that are labeled in red. That has not quite happened. That's the bad news, but there's good news too. You can see here the red boxes are the coal-related carbon sequestration projects that were, and you can see there's almost no coal-related carbon sequestration projects left. That's the bad news, except the 2 red circles that you see in the middle on the right. But instead of that, there have been a number of carbon sequestration projects that were related to gas production. And the reason for that is that when you produce natural gas, you often produce a lot of CO2 with your methane. And you have to separate these 2 gases, so you need to separate the methane and the CO2. And then you can take the CO2 and inject it back into the subsurface. And the other examples where carbon is being stored in the subsurface is for the production of hydrogen. Hydrogen is often touted as a clean source of energy. And it can be, but it depends where the hydrogen comes from. There's 2 ways of making hydrogen. Green hydrogen is you take water and you basically, you have electrodes with a positive and a negative voltage, and that splits the water into hydrogen and oxygen. And then that's a way of converting electricity into hydrogen gas. So if you have a lot of electricity from solar or wind or geothermal, then you can make energy, you can create hydrogen, which is a very clean source. You burn the hydrogen in your car or whatever it would be, and then you just end up with water. Most hydrogen that's being produced right now isn't produced like that. Most hydrogen that is produced right now is produced from natural gas. So you have 1 carbon atom, 4 hydrogen atoms around it. You basically split the hydrogen from the carbon. That takes energy, of course. The carbon is burned in the process, becomes CO2. So that's not green hydrogen, right? It's called gray hydrogen. So it's that hydrogen that is now, or the CO2 that is produced in that type of hydrogen production that is being used for current sequestration projects. But the main point here is that, if you add up all those circles, you don't get anywhere close to a gigaton per year. The biggest circle is 5 megatons per year, right? That's 1/200th of a gigaton. And so I also looked for data. How much CO2 are we storing right now? Where are we heading? And so this is from a recent paper, 2021. This shows the amount of the cumulative CO2 stored in the subsurface as a function of time, from 1972 to 2035. You see a black area and a green area. The black area is carbon dioxide that we currently are injecting in the subsurface because we use it for oil production. So if you produce a reservoir, a petroleum reservoir, the pressure tends to drop, and to maintain the oil production you have to jack up the pressure, and one way to do that is to inject carbon dioxide into the reservoir. It's a well-established technique, so it works very well. And you can see that most of the CO2 that we inject right now in the subsurface is connected to, it's called enhanced oil recovery, injection of CO2 into petroleum reservoirs. And then the green area gives us the dedicated sequestration projects that are in place right now. You can see it's much smaller than the black area. But then I asked myself, okay, so how much are we now injecting in the subsurface? And so currently it's about 0.04 gigatons per year. Now remember, how much was one wedge? How much gigatons of CO2 was it per year? 3, right? So we are short by a factor of 100. And it's forecasted to increase to 0.1 gigatons per year, which is still a factor of 30 smaller than one wedge. Now, it's still CO2 removed from the atmosphere, so, it contributes, but it's about 1/30th of what we need to do for one wedge, which is only 1/7 of all the things that we need to do, and that was from the scenario of 2004. But the more recent scenario for 2013 said, okay, we have to sequester about 3 times as much. So, currently we're not on track to get anywhere close with carbon sequestration to basically cover one wedge. Of course, it makes a difference what we are doing. But to call this a leading mitigation technology, I think, is an over-optimistic view of looking at it. So why is this not getting larger? Right? And I think the answer is cost. cost. So here you see the cost of capturing and injecting 1 ton of carbon dioxide in the subsurface. And units are dollars per ton. So if you look at the bottom row, it gives a total cost. It's anywhere between $30 or $70 per ton. And it's interesting to see how that is split up. It's split up into capture. So basically, how do you capture the CO2 out of the gas that you have? Transportation, you have to stick it in pipelines and transport it, move it around. Then there is the storage itself, so you need to build facilities to inject the CO2, and then you need to monitor it. And you can see that by far the largest cost is the carbon capture. Right? How do you extract the carbon from the atmosphere or from the waste stream that you are using? So the challenge in carbon capture and sequestration is basically a chemical engineering challenge, because the biggest cost is capturing it from the gas that you have, and that is by far the most costly component of the whole endeavor. Okay, and I asked, these are fairly old numbers. These are from 2005. I asked, has this changed? So here you see data from a more recent paper, 2020. Again, the total cost here for carbon sequestration, depending on the scenario that you go for, is again between $50 and $60 per ton. So it's relatively expensive, and I'll show you in a minute that it's the most expensive option from everything that we can do. Why do we need to capture the CO2? Well, if you look at, for example, the composition of gas that comes out of the tailpipe of a coal-fired power plant, it's about 10% of CO2. It's about 5% water, and those are combustion products of burning coal. 10% water. There's a little bit of oxygen left. Right now we breathe about 20% oxygen, but most of that oxygen is burned in the power plant, so there's 5% oxygen coming out of the tailpipe. And the biggest gas is nitrogen. And that shouldn't surprise us, because right now, we are breathing an atmosphere which consists of 80% nitrogen. So you can see, of course, if you don't separate the CO2 from the other gases, you're going to have 10 times as much gas volume as when you have separated the CO2. So first of all, there's the problem with the volume. So if you don't separate the CO2 from the other gases, you need to sequester about 10 times as much material. Right? And it's already an issue where we're going to leave that stuff as we're going to inject it. Well, that problem would be 10 times as large. But there's another problem. Carbon dioxide is heavier than nitrogen. So the boiling point of carbon dioxide is much higher than it is for nitrogen. So basically, if you want to compress everything to a liquid, you also have to compress the nitrogen. But that is a very difficult job to do. That takes a lot of energy too. So you really need to, there's many reasons why you need to separate the CO2 from the other gases. Now the gas separation, there's many different scenarios for it. I'm not a specialist in any of it. But you can either press the gas through a suitable membrane. Of course, that takes a lot of energy because you have to push the gas through a membrane, just like with desalination. It takes a lot of energy. You can use chemicals that absorb the CO2, and then if you supply energy, then they release the CO2 again, so that is, you use a sorbent, so to speak. Or you can basically you can distill, so you cool down the air until the carbon dioxide and the nitrogen, they separate in the gas and the fluid, and then you can separate them. All of that takes a lot of power and energy. And in fact, if you look at carbon capture and sequestration, what this graph tells us, it's a complicated graph, but it basically means that if you're going to capture the CO2 from, in this case, a coal-fired power plant, 30% of the energy that you've generated to start with is going to be needed to separate the CO2 from the other gases. So it's a very energy inefficient process. Now, if you have enough hydrocarbons, you might say, okay, that's okay. 30% of the energy that I've produced, I'm going to use again to capture the carbon out of the air. But it's a very energy inefficient process, and thereby also a very costly process. And that explains that $50 per ton of carbon sequestration. And so that's I think, I want to phrase this like a number of challenges, research challenges, like how can we reduce the cost of carbon capture and sequestration? And the biggest cost is, of course, the cost of carbon capture. And I think if this is going to work, we just have to be more intelligent than we are right now. I mean, this is obviously a large problem. Plants figured it out, right? I mean, plants are really good at capturing carbon dioxide at room temperature. Yes, it takes energy. That's the sunlight that they absorb. But plants know how to do it. So one of the main research challenges that I see is to reduce the cost of carbon capture and sequestration. And there may be lots of interesting scenarios that we haven't looked at yet. The other thing is, I want to come back to how much are we injecting right now. So currently injection rates are in the order of megatons of CO2 per year, 5 megatons, you know, and but we have to inject about 3 gigatons of CO2 per year to cover one wedge. So that is 3,000 megatons. And that leads me to the second question, is how do we upscale the current technology? We need to upscale it with about a factor of 3,000. Now maybe the answer is, you take a platform like this is the Sleipner platform in the North Sea. It's a platform for gas production. So gas is being produced. A lot of carbon dioxide is co-produced with the gas. They separate the methane, natural gas, from the carbon dioxide, and the carbon dioxide goes back into the subsurface. And this is paid largely by subsidies from the Norwegian government. So maybe we need 3,000 of these facilities. You know, maybe the answer is to upscale this. Okay, we just need to build more facilities. I don't know. But I think that's the second research question that I think we face is, how do we upscale the current technology with about a factor of 1,000? I don't think we know how to do that. And maybe the answer is, well, you just build 1,000 times more facilities. But if we really want to make a difference in in reducing the amount of carbon dioxide emissions into the atmosphere, that's the challenge that we face, if we want this technology to be a major contributor. Here's the third challenge. You know, geophysicists have done an amazing job in imaging the subsurface, and they also did an amazing job in imaging time-dependent changes in the subsurface. So here you see images of the area where carbon dioxide is being injected at the Sleipner platform. That's the platform that I just showed you. So they shot seismic surveys, in this case between 1994 and 2008, and you can see these images that are developing over time. That's an imprint of the CO2 in the subsurface as we see it in the seismic data. So it's impressive that we can see this. It's impressive that we can see the carbon dioxide. It's impressive that we can see how it migrates in the subsurface. So this is pretty amazing. But to measure these time-lapse changes, for these time-lapse changes measurements to be useful, we need to do them with a very, very high accuracy. And why is this? Well, if you inject carbon dioxide in the subsurface, it reacts with the rocks there. You know, carbon dioxide is being absorbed by rocks in weathering processes. That's a natural process. And depending on the rock type and the temperature, it takes about 200 years for the CO2 to react with the rock. So by that time, it's become a solid. We're never going to see it again. Right? So that's one of the main ideas of carbon capture and sequestration, that it actually reacts with the subsurface, and it becomes basically a solid, and we're not going to see it back. That's the good news. The bad news is you have to keep it there for 200 years for this to happen. So I asked myself, okay, for different leakage rates, how much do we lose? So if you lose 1% of the CO2 per year, every year for 200 years, you've lost 86%. Basically, all of it is gone. Right? And if you lose 0.1% per year, you lose about 20% of the CO2. But let's say 1%. Let's say, okay, if I would lose 1%, that's bad. Because by that time, in 200 years, basically all of it is gone again. Right? So that also means then, for our seismic monitoring methods, they have to work with an accuracy of being able to monitor a loss rate of 1% of CO2 in your reservoir. That is not a big amount. I mean, that's a huge challenge. And then I think that's the third research challenge that we face is, Okay, how do we monitor and predict extremely low leakage rates? I don't think we are there as a geophysics community to monitor these very low rates. So this is the third research challenge. So I may have really depressed you by now. There's also good news. So let's talk about the good news. We are incredibly wasteful in our energy use. This is a very complicated graph. It's from the Department of Energy. And on the left side, it describes the different sources of energy. So there is natural gas, coal, petroleum, nuclear, etc. It's all coming in. It's being used for different purposes. And then all the way on the right is being divided into useful energy and lost energy. And you can see that about 60% of the energy that we produce is being lost. It's basically all gone. You know, it's energy losses in the power grid. It is, we have a limited thermodynamic efficiency in power plants. And of course, you will always lose energy. You cannot produce energy and have 100% efficiency. But we can be much more clever than we are right now. You know, I stayed in a hotel recently. It had 2 heating, cooling units and 2 thermostats. Okay? One of the thermostats was set at 68 degrees Fahrenheit, and the other one at 72 degrees Fahrenheit. So you know what? The thermostat set at 68 degrees led to a jet of warm air being blasted into my room, and the thermostat set at 72 degrees was blasting a jet of cold air into my room. Right? And this was not an old hotel. This was not a renovated old hotel. This was newly built. We still build things like that. You know, and here I think we can learn a lot from Europe. In the Netherlands now, there's a whole project going on to basically not supply natural gas anymore for heating at homes. And they're building very energy efficient homes. You can even build energy efficient homes in a place like Colorado, which can be a pretty cold place, that don't need a heating system anymore, that are very comfortable. And you can use heat pump technology. I mean, they still use some energy, but they use much, much less energy than we do right now. So we can be much, much more intelligent than we are right now. It's going to take some money. It's going to take some investments, but we can make big savings right there. This is a study that I find absolutely stunning, and it's done by McKinsey, so the big business consulting company. This is a very complicated graph, so don't worry, I'm going to simplify it. But all these bars here are different steps that we could take to avoid carbon dioxide emissions. And the width of each bar gives us how much the United States would avoid in carbon dioxide emissions if we implemented those steps on a big scale. And the vertical axis gives us the cost of this, the long-term cost. So this is a very complicated graph, so I simplified it, but the numbers that I'm going to show you in the simplified graph are roughly the same as what you see here. So again, it's the same graph now, but simplified. So again, the width of each of these steps that we take, so let's say electronics and lighting, efficient cars and trucks, efficient new buildings, the width of every step is the amount of carbon dioxide emissions avoided by the United States if we adopt the technology on a large scale. The scale goes to 3 gigatons per year. Sounds familiar? That's one wedge, right? Or if you want to look at it a different way, the United States produces about 7 gigatons of carbon dioxide per year. So if the United States implements these steps on a large scale, we avoid about half of the CO2 emissions that we currently have. That's huge, right? That's a big change. The vertical axis gives us the cost of these steps in dollars per ton. Okay. So again, on the right you see carbon sequestration, $50 per ton, right? That's the numbers that I've just shown you. So that's also shown by the McKinsey study. But you see, all the bars indicated in green, they have a negative cost. We can save money. We can save money. Okay? These are steps that pay for themselves. Now, the bad news is this is the long-term cost. So to get these gains, we first need to invest. Right? So we don't just get these savings in year one. And so you may need government subsidies and incentives to make this happen. But on the long term, you save cost. How does this work? Well, if you use LEDs for lighting instead of the traditional incandescent light bulbs, your energy bill goes down. So the initial investment in the light bulb is a little higher, but on the long run you save money. We are already doing that on a large scale. Right? Who still buys the old light bulbs? I guess very few of you do. There's also the steps indicated in blue are the steps that are not going to pay for themselves on the long run. That doesn't mean we shouldn't go for these. It's just that they will not pay for themselves. So let's say, improve existing buildings, for example. That can be an expensive proposition. So to make a new building energy efficient is relatively cheap. To renovate an old building is much more expensive. And some of this study is about 10 years old. Some of the data has changed. Renewable energy here is still listed as a positive cost. But by now solar energy is competing with coal in terms of cost. Those costs have come down a lot. The main point I want to show you this is if we would implement this in the United States on a large scale, we've done one wedge. And then there's Canada who could do something similar. And so collectively we could do a lot. And actually the total long-term cost of all of this, so mathematical jargon, the integral of this curve is actually slightly negative. We would save money. But carbon sequestration is the most expensive option of all. Right now, unless we can solve, of course, some of these challenges that we have, and we might be able to. So, just to summarize, right? I mean, these are what I see as the main questions for carbon capture and sequestration. Right? How do you reduce the cost? And that's basically a chemical engineering problem, or going for sources of CO2 that contain more CO2 as a volume fraction. Than what we do right now. How do we upscale the current technology with about a factor of 1,000? And how do we monitor and predict extremely low leakage rates? So let's now go to the indulgence. I think there's a danger in some of this technology. And I say this with some trepidation because the argument is a bit, it shouldn't paralyze us, my argument. But when Martin Luther started the Reformation, he basically nailed his 95 statements at the door of the church in Wittenberg. And one of the things he rebelled against was indulgence. So what is indulgence? Basically, if you had sinned, you could pay the Catholic Church and you would be absolved of your sin. Right? So if you're rich, you could be a bastard, but hey, you would be forgiven because you gave a lot of money to the church. That was one of the things he rebelled against. So that was called indulgence. What does this have to do with carbon capture and sequestration? There is a certain risk that by doing a small thing, you may think you may have done your job without really solving the problem. So let me give you one example. I mentioned earlier that flying is about the worst thing that we do. Okay? I know people who like to use the new train that goes from Denver to the airport, and they feel really good because they take a train. I'm not using my car. Great. And then they fly to Thailand or Vietnam. Right? So if taking the train becomes now the argument that you use for yourself to say, okay, it's okay to fly to Southeast Asia because I've taken the train from downtown Denver to the airport, right? I mean, the net impact on climate change is still very negative. Right? So that's the risk that you run by doing projects that make a little difference and they make you feel good. And then you say, okay, I've done my job, I'm done. Right? Now, that's not an argument against carbon capture or sequestration, because we still make a difference. Every megaton injected is 1 megaton. But you now have the big picture of that imprint is pretty small. So if that creates a sense of complacency, like, okay, I've done my job, now I can get into my car, or I can get on the plane, or do whatever I do to burn hydrocarbons, that's a dangerous argument. So I don't think that carbon capture and sequestration is a miracle cure. It's not a panacea. We also have to be careful that we don't treat it like an indulgence, that it makes us feel good, and now we've done our job, we're done. Right? It makes a difference, but it's a relatively small difference, and we need to be aware of that. It's very interesting to look at sort of different types of problems. If you look at the problems that we have, they can either be technical problems. So technical problems is a problem where we have the expertise, we know how to move forward, we need to manage it somehow, we're going to require resources, and then we have to do it as efficiently as possible, we have to optimize execution. Those are technical problems. There's many problems that we have which are of this nature. By contrast, you also have adaptive problems. So for an adaptive problem, expertise is not available. We still need to develop the expertise, we need to do research, we need to move forward. To execute the plan, it's going to require learning because we don't quite know what the path is yet. Adaptive problems need leadership, not management. This is why, some people are great managers and poor leaders, and some leaders are poor managers. I'm a lousy manager. You don't want me as a manager, believe me. I don't know if I'm a good leader either, but and adaptive problems, they don't just require resources, they require change. And to deal with an adaptive problem, it's going to require experimentation and risk. And I want to highlight these, require resources and require change. First of all, climate change is a problem, I think it's truly an adaptive problem. Right? But there's technical components to it. But it really calls us to consider what is the society that we want to build and how do we want to build that society and how do we want to live, how do we create a lifestyle that works for us and that is truly sustainable, right? And that is to a certain extent a technical problem, developing sources of renewable energy, whatever it is, right? But largely it's also an adaptive problem. And this is why I highlighted the blue box, because the technical problems require resources. In a way, that's the easy part. It's easy to say, we're going to invest so many $100 million in a new technology. Right? That's relatively easy. Also for a politician, that's relatively easy. It still may be a hard sell with decision makers, but it's not an emotionally charged project. But adaptive problems require change. And we are all for change. I'm all for change, as long as I don't have to change, right? Anybody recognize this? Right. And so this is what climate change calls us for. It's both a technical problem and an adaptive problem, and we're going to need resources to work on it, but we also may have to change. But there's wonderful things that can be done. This is the Department of Environmental Study at the ANZA Community College. They built an energy efficient building. They're saving $65,000 per year in the cost of running the building. And they're not just running the building, they designed the building in such a way that the whole energy system is visible. You can see on the lower right, behind plexiglass, you see some of the facilities that they use or some of the equipment that they use to manage the energy. And who manages the energy? The students. Every week, a different team of students is being charged with managing the energy of the building. And of course, they all are competing with each other because they want to reduce the amount of energy used in that particular week. I think this is a great example of building new technology and also using it as an educational tool to show what can be done by making more intelligent buildings. I also think that as an educator, we have a role to play. I think energy education has to be a big part of the solution. We need to understand this. And I love this quote, a student is not an input. So I want to read it with you. I think we have the responsibility to insist that education is more than learning job skills, that it is also the bedrock of a democracy. I think we must be very careful that in the race to become wealthier, more prestigious, and to be ranked number one, we don't lose sight of the real purpose of education, which is to make people free, to give them the grounding they need to think for themselves and participate as intelligent members of a free society. And as educators, I'm speaking here at the University of Toronto, I want to share this quote with you because I think it speaks to our role as educators in society. And so it is for this reason that I built this lecture. It's called the Global Energy Challenge. I've given it more than 120 times at universities, churches, service clubs, schools, high schools, middle schools, you name it. And because I think education has to be part of the solution. And this is the favorite slide that I show in the Global Energy Challenge. So this is a quiz. So let's do the quiz right now. So here you see one of the trains with coals that you can carrying coal that drive through Colorado all the time. And one car of the train contains about 100 tons of coal. If I burn those 100 tons of coal, how much CO2 do I produce? I have a hard time seeing you with the lights in my face, but does anybody want to venture a guess? Multiply by 3, and that's the right answer, right? So it becomes 300 tons. The answer that I get most of the time is a few ounces. And I ask, why a few ounces? And people say, well, it's a gas, it's light. Well, you laugh, but you know, it's hard to think of gases as being heavy, but like nobody, if I would take all the air in this room and I would compress it to a liquid basically, none of us would be able to lift it because it would be several tons, right? I mean, air is heavy. That's why planes can fly. Air is not light. It's light compared to water, right? And why is it a factor of 3? And I can explain this to middle schoolers. You take one carbon atom, it connects to 2 oxygen atoms, CO2, and oxygen and carbon have about the same atomic mass, and so it becomes 3 times as heavy. And so these are simple things you can do to educate and to help create an awareness of what we are doing in our behavior. So if you do the math, right, per mile that you drive, you produce about 1 pound of CO2. That's a lot, right? I mean, now think about a road trip of 1,000 miles. You can do the math. So I think by helping to create an understanding of the numbers and to make a connection between our behavior and the impact that it has may change our behavior. I don't know if it will, but this is something that is in our span of control as educators. So to conclude, I think carbon capture and sequestration is not a panacea. It can be some contributor to sort of mitigating climate change, but it's not going to be something that is going to be a major change unless we have a major breakthrough in technology. Is it an indulgence? No, not necessarily, but it depends how we present it. If we present it as geoscientists, like, you know, we are doing carbon capture and sequestration, we've done our job, I think that's an oversimplification, at least right now with the current state of technology. I think carbon capture and sequestration makes most sense for enhanced oil recovery, because then there is a business driver for the whole process. Or when CO2 is co-produced with natural gas, or if you can have another source of carbon dioxide, which is much more concentrated than what you find, let's say, in the tailpipe of a nuclear power plant. And you probably are going to need some tax incentives or subsidies to make it work. And that can happen. Those are political choices that we need to make. And here again, you see the main research questions. We talked about that. So to end, I want to switch. I'm an educator at heart. I want to briefly introduce you to 2 educational pet projects that I have nothing to do with carbon capture or sequestration, but I wanted to introduce these to you because I'm very excited about these, and if anybody wants to collaborate on any of these projects, I would love it. So the first is I've developed the course Science and Spirituality. And you see in blue, you see the topics that I cover in the course of Science and Spirituality. It's an elective that I teach now at the Colorado School of Mines. It's a very popular course. The class fills up in like 30 minutes after students can register. And I think it is because our young people, we raise them currently on a staple diet of scientism. And science is great, but scientism is basically, you describe the world in terms of the current science that we have, and if you can explain something, then it's not there. Right? That's scientism. That's what we currently basically teach at universities, or at least we stay quiet about everything that falls outside the traditional boundaries of science. And our young people, they have a much broader interest. They have a much broader interest. They think about the questions of life and death. They think about questions like, you know, who am I? What is my consciousness? If I raise my arm, what really is going on? And who makes the decision that I raise my arm? Right? Things like that. So I found that students are really really hungry for this topic. This is obviously not a topic for every student. This is probably being a subset of our population that is interested in it. But I have a great passion for teaching this class. The students love it. If anybody wants to collaborate on this topic, I would absolutely love it. And there's a website here where you can find more information about this class. I put in these 3 images. In the middle image, that's us as humans, right? This is somebody walking the labyrinth, which is like a walking meditation. And we're sort of caught between the very large on the left. You see a galaxy here, which we don't really understand, right? And I don't know about you, but if I see those images from the Webb Space Telescope, I'm just filled with awe. You know, I think, how is this possible? And on the right, you see the quantum world, which we also don't understand very well. We can make wonderful calculations, but what it really means, we don't really know. And in between, we're caught between these two, between the infinitely large and the infinitely small. And I think that's truly fascinating. The other project that I have is teaching with heart. You know, if I see students go through university educations, they are put under a lot of pressure, and you know those pressures are there, and they're part of learning to have expectations and having to live up to those expectations. But it doesn't mean that we should be uncaring as teachers. And I'm not saying that we are uncaring as teachers. We have plenty of caring teachers everywhere around, right? But how can you teach in STEM fields, in technical fields, in higher education, and do this in a way that actually nurtures the students? They might even learn better. We don't really know, you know? I mean, do we need to crack the whip to make them run? I'm not sure. And so I'm also working on this project, which is partly research, but it's partly also training of teachers and experimenting with teaching techniques that bring a more heartfelt attitude to STEM fields, science, technology, engineering and mathematics in higher education. So if you're interested in this, there's a website below. I'm also looking for collaborators. If you want to join me in some way, I would love it. So with that, I'd like to end my presentation. I want to thank you for your attention. I don't know if you want to take questions or... So, you're driving now.
Intriguing talk, and we'll open up the floor for questions. There are microphones over there. You feel free to walk up and take the microphone. Yes, please go ahead. If we could double the number of trees and plants, what difference would it make to our CO2 sequestration?
Okay, so the question is if we could double the amount of trees and plants, let's say take desert areas and plant forests and make sure the forests are actually thriving, what difference would it make? You know, I don't quite know the answer because, of course, plant life is partly on land and partly in the ocean. Right? There's a lot of algae living in the ocean that do photosynthesis and that absorb CO2. So I don't know. I do know that if you look at all the carbon streams from the atmosphere to the ocean and between the solid earth and the atmosphere and things like that, those carbon fluxes, the carbon streams, are very large compared to what we produce as humans. So we make a small difference in the carbon balance in the atmosphere, but that's enough to drive the change in CO2 that we see right now. That's a complicated way of answering your question with, I don't know. Yeah, I just don't know.
It would be significant, or
I don't know. Yeah. My guess is it would be, but I think it would be quite a challenge, of course. But I'm guessing now. Of course, right now we are destroying a lot of the forests, and especially in the tropical areas. So we're doing exactly the reverse. And,
thanks for the terrific expanding our knowledge and awareness. And all of the sequestration projects were point sources in your power plant or whatever. Yeah. There's been some press on capturing it from the air, which would be a huge technological feat because you've got parts per million.
Yeah.
What news do you have on that front?
Well, it seems to me it's much easier to capture CO2 if you have a gas stream that is, let's say, 10% CO2 than when it is, let's say 500 parts per million, which is much, much smaller. So it seems to me that unless you have a natural process to do that somehow, it seems to me a very inefficient way of doing it. Now, of course, there have been lots of alternative technologies proposed to basically absorb CO2 from the atmosphere. And rocks do this, right? I mean, when rocks weather, they absorb CO2 from the atmosphere. So there have been proposals to basically use finely ground rocks to basically make those rocks interact with the atmosphere and then absorb the CO2. And maybe even use those in agriculture. There's proposals floating around, and maybe that makes a difference. But again, think about it. One wedge is 3 gigatons of CO2 per year. And if you want to make that CO2 react with a rock, you probably need a multitude of that 3 gigatons per year to do. So upscaling these technologies, I think, is the hard part. But like the projects that are going on in Iceland now to basically scrub the CO2 out of the atmosphere, well, I'm not a chemical scientist, but to me it sounds a very inefficient way of doing it. Unless you can have a really clever trick to basically bypass thermodynamics. Well, by the way, I say this now, but it's pretty amazing what plants do, right? It's pretty amazing what you do right now. You are burning sugar at this very moment. If I give you a cube of sugar, and I put it in your hand and I say, okay, burn it at room temperature, you say, I don't know how to do it, but this is what you're doing right now, because you have clever catalysis going on in your body that makes it happen. That's how we live. So I'm not saying it's hopeless.
So maybe I'm just ignorant on this, but suppose we did manage to get the 9 or 21 or however many gigatons per year, what exactly would that guarantee for the future of the climate?
Well, it comes back to that. Okay, so what we can do, if we would implement all those 7 wedges, then we keep the carbon dioxide concentration in the atmosphere at 500 parts per million. And you might say, well, what would that do? First of all, we're not there yet, right? So anything that we see right now is not going to go away. So those 500 parts per million would lead to an increase in the temperature, global average temperature on Earth between 1.5 and 2 degrees Celsius. Again, that's the average temperature. But you would still see the same types of sort of climate variations and variability that we see right now. We're not yet at 500 parts per million, right? We're at 420 parts per million, and we already are seeing a lot of changes. So you would still see, global warming and all the phenomena that go with it, and they probably would be more extreme than they are right now, but you prevent it from getting worse than that. Yeah. So this is a great question, because if you work on those 7 wedges, you haven't solved the problem yet, at least.
So this is going above.
Okay, there you are.
Yeah.
I have a hard time seeing you. That's why I'm sort of squinting at times.
So this is about the other 7 wedges. Do you personally see any other? Because we saw that the sequestration is maybe 1/10 of that wedge. Do you see any other wedges that you could see as actually practically feasible within? Yeah.
Well, it's actually very interesting to go back to the paper of Pakala and Sokolov, because they give 15 possible wedges. So they just divide it into 7 to make the problem manageable, but you could implement 15 wedges. And I think one of the things we sort of need to look at is nuclear energy. I don't like it. It scares me, but it scares most of us. But maybe we are also too dogmatic in discarding it. I don't know. In terms of renewable energy, there's of course a lot happening right now. Price of solar coming down, the wind energy. There's a big plan in the Netherlands to build gigantic solar farms in the North Sea to produce hydrogen. So basically the idea is that at the wind turbines, you produce electricity. You have plenty of water around because they're it's a gigantic park in the North Sea. You use the water to, use the electricity to split the water into hydrogen and oxygen. You take the oxygen and you pipe it onshore, and then you can use it for transportation or other purposes, right? So I think there's a lot of creative engineering solutions we can go for, and how many of these are affordable and realistic? It's difficult to answer that question. I'm not an expert on this, so. Could you use the microphone, then we can, because I know you can hear your voice, but your mouth is very close to your ear.
It's about a decade ago or so, there was quite a bit of interest in trying to stimulate processes in the ocean.
Yeah.
And cause it to sequester
Yeah.
carbon dioxide.
Yeah.
I haven't heard anything about that in the past 2 years.
Yeah.
Did that all turn out into something, into nothing?
Well, so what you were referring to is a very broad scale of technologies which is called geoengineering. Basically, you start engineering the climate. So one of the ways is to basically fertilize the ocean, dump iron into the ocean. If iron is the limiting factor for basically algae for absorbing CO2, then it can promote the growth of algae, and that can absorb more CO2. There's one example of geoengineering. A related proposal is to inject sulfuric acid into the stratosphere, which will actually block sunlight, so there's less radiation coming down into the lower parts of the stratosphere. On a big scale, those technologies probably do something, but they also raise a lot of interesting questions. Like, for example, suppose you can do that. Suppose you can control the temperature on Earth. Right? Who controls the thermostat? Is it Canada or is it Mexico? Right? They both benefit and are hurt in different ways by changes in temperature. So there's a whole bunch of ethical questions related to that. That doesn't mean that those technologies don't work, but they also raise lots of other questions. So I don't know about the specific projects for fertilizing the oceans. That is one of those many techniques for geoengineering, and there's lots of interesting issues associated with them. Yeah.
And I just want to quickly remind, there's about 50 actually online audience. If you want to put in your question, I see there's one on Q&A, actually 2 on Q&A here, or the YouTube live stream. Feel free to go ahead, and we'll hopefully cover some of your questions later. Oh, but sorry, go ahead.
Did you want the mic? Can you pass that to him?
Hi there, and thank you for your talk. When you showed us the images of the seismic graphs of that oil field in Norway, and then you presented the loss rates and then the relative cumulative loss over 200 years. Do we have any idea what the current loss rates are from existing carbon capture facilities?
You know, that's a great question, and I'm giving you a lot of I don't know answers, by the way. And the short answer is, you know, I don't really know. We see at Sleipner, we see that it migrates it slowly migrates upward, at least as far what we can detect. And the thing is, of course, at what point does the CO2 reach a cap rock through which it cannot propagate anymore? Right? Because it may be that it is moving and it is slowly moving, it's slowly migrating upward, but it doesn't mean it's going to migrate upward forever. Right? And this, because we know the Earth can hold down gas. Right? I mean, the Earth is very good at containing natural gas. I don't know if you read the last issue of Science magazine, but there's a fascinating article about just hydrogen gas seeping out of the Earth, and you know, and I don't know if this is a big thing or an exotic phenomenon, but the Earth can contain gases, and so I think my impression is that at Sleipner we don't quite know. You know, what the image that I showed you was changes in seismic velocity. To what levels of concentration of migrated CO2 that does correspond, I don't quite know. But even then, you need to figure out, okay, is there at one point going to be a cap rock that is going to keep it in place for long enough for it to react? And I don't know the answer to that question.
Maybe we can check the online Q&A there.
But I cannot see the...
There's Q&A here.
Okay.
Click on that.
Will read it out to you.
Oh, okay. Pius is going to read us. Yeah.
Okay.
It's small to see.
So first question from Christopher Matzner. In Canada and elsewhere, the fossil industry and right-wing think tanks use misinformation, disinformation, and greenwashing to prevent governmental action that will stimulate an energy transition. At the moment, policy decisions are being made under the assumption that CCS is a viable alternative to renewables. If CCS is intrinsically more expensive and renewable energy is now significantly cheaper than burning coal or oil in the first place, then why are you working and speaking on CCS at all?
Okay, well, first of all, questioner online, I don't work on CCS, and I'm not submitting proposals to the Department of Energy to work on CCS, because this is exactly the concern that I have, that, you know, by spending some money on the technology, we think like, okay, we've done enough. And so I'm not working on carbon capture and sequestration. Regarding the question about the industry, that's a very valid question. You know, there was an article in Science magazine 2 months ago, I think, about studies done by ExxonMobil on climate change scenarios, and those were, I believe, from the 80s and 90s. You know, they were amazing studies on making projections for climate change, even though the company as a whole was just denying a connection between CO2 production and changing climate. And you know, the word greenwashing was used. That's indeed a danger of using a technology now that makes a very small difference, but which is not enough to make a really sizable difference, but using that as an excuse to basically not do the things that we have to do. But I'm here to inform the public about this. You know, this is why I've decided to fly over here, even though I have a reservation about flying, because I think we need to talk about these issues.
Right. The next question, could you expand on the danger of injecting sulfur into the atmosphere?
Okay. I'm not an atmospheric scientist, so maybe, you know, Kim would be much more qualified to speak about what sort of side effects there might be, or what unintended consequences there might be from a physical or a chemical point of view. But there's the whole issue of geoengineering, like, you know, who's in control? How much sulfuric acid are you going to inject into the stratosphere? And again, is it Canada or Mexico, or who decides what the final temperature is going to be? If the technique would work actually to as a thermostat for keeping our climate at a certain temperature. That's one of the main issues that I see. I can refer whoever asked the question to a paper that lists all the ethical issues of geoengineering, which is a very interesting issue in itself.
Okay, so maybe we'll take one last question from the audience here. Looks like we don't have any online questions.
No, you can't. No. You need a microphone.
Okay. So my question is so we know that fracking causes, you know, disturbances in the land that end up with, you know, Texas, for example, being a lot more seismically active. Mm-hmm. Would injecting carbon into the ground have a similar impact as well?
My guess is that it would. You're changing local pressure state. But here's something to keep in mind. I don't want to belittle the concerns about seismic activity. Right? Making decisions about our energy system is very difficult, right? And we tend to focus on what we don't want. And that's good. It's good to be concerned with what we don't want, right? Nobody wants earthquakes in Oklahoma, obviously, or in the northeast of the Netherlands. So that is a valid concern, right? But there always is something. Right? With nuclear energy, we have a concern about the storage, which is a real concern. With wind turbines, we worry about, migrating birds being killed, which is a valid concern too. And we tend to focus in our decision making on the things that we don't want. And I'm not saying that we should be ignorant of those issues. We should take them into account. Right? But we should balance them in a rational way with the things that we do want, right? I mean, we're all happy here that we are sitting in a heated room and that the light is on and things like that. And I have a separate talk about, differences in perceptions and decision making about hydraulic fracturing in North America and Europe, which is completely different. And I think we sort of need to learn how to make rational decisions to balance the things that we don't want, which are real valid concerns. I don't want to belittle them, but the things that we do want. And right now, a lot of the conversation is driven by groups pointing out, I don't want this or I don't want that, right? And then it becomes a power game, like who wins. I'm not sure I answer your question. I made the problem a little bit bigger. But,
thank you very much for answering those questions, Roel. And also thank you, the audience, for taking the trip and here, and then hopefully you'll enjoy the evening. And we'll actually have refreshments. Actually, I just was told that upstairs, so instead of outside, as we had in the previous years. So feel free to join the refreshments and reconnect with your colleagues or longtime friends here, and also to talk to our speaker. So we'll take the one last opportunity to thank Roel for flying over to give the public lecture. Thank you very much.